Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to answer the following question: what is a heat engine? So some of the pictures we're looking at, let me start on the right hand side here. So here's kind of a picture of an automobile, and this orange spot in here is supposed to represent what's happening inside the engine of that automobile. Now don't worry about like how many pistons or whatnot. Just for now, it's realize this, that fuel is combusted, and that creates a large heat transfer as represented by this orange here. So we have a very hot region inside the motor. Now some other things to consider. This automobile ultimately has an exhaust, and that's going to carry hot air along. That's represented in red here, and we're going to have some energy leaving the system out the tailpipe, represented by the red here. Now also the engine, what it does is it applies what's called a torque to the drive shaft, which ultimately creates a force between the tire and the car and moves the car down the road. So if I think about what's happening here, we have an energy input in the form of the combustion of fuel. We have an energy leaving the system in the form of hot air leaving the exhaust, and we have work being done. Now technically the work is a torque applied to the drive shaft, and then when the drive shaft starts turning, that's the work done. But for this video, I want to keep it as simple as possible. I'll just say this, that there's a force created now between the tire and the road, and then when the car starts moving, there's work done. That's a very important part of that picture. So if we think about what is the role of the engine here, basically it's converting the energy stored in the gasoline to mechanical work, making the car go down the road. Right? In this picture, we got kind of a picture of a ship, and presumably it's maybe driven by a steam engine. Just from the picture that I took here, it had some kind of dark clouds coming out of it. So somewhere down in the guts of this ship, there is a vessel or container where the coal is being combusted, and then we're going to have a lot of heat transfer there, and I've represented that in orange. Ultimately, the role of the engine of the ship is to turn the propeller. So in order to do that, you have to apply a torque or a force to get the propeller to turn. So the engine of the ship, if you will, is doing work turning the propeller. Also notice that a lot of air is going to leave off the stack, and this air is going to be very hot here. So I've represented a heat transfer here in red. That's a loss in the system. So we have an energy input in the form of combustion of coal. We have an energy leaving the system in the form of exhaust, and we have work being done when we turn the drive shaft or the propeller. Rocket engine, same deal. Okay, within the rocket itself, right, we have some sort of rocket combustion, rocket fuel combustion happening in this region somewhere, and then the fuel heats up air, which goes shooting out the back, creates a force up on the rocket. Now when the rocket starts moving, there's work being done because you've got force times distance, and you'll notice we have a lot of heat leaving the system, which I represented in red here. Right, we got a lot of heat leaving in this case. Here we have a picture of a person riding a bike. Now, a very similar thing is happening here. There is, believe it or not, a heat source here. As a person does exercise, they are doing work. So, for example, he's pedaling, so this person is applying a force down on the pedal. So there's work being done. The energy source is the combustion of calories that are stored within him. And when the person breathes, there's warm air leaving the system. So you'll notice that all four of these examples, they have some sort of energy input, and they are all combustion examples. There's an energy output. Every one of these has an exhaust, including the person, and there's work being done. So these are all examples of what are called heat engines. A heat engine is any device that takes heat from a hot source and converts some of it to work. There's a picture that describes what a heat engine does. It's just a quick little schematic here. So, oops, I'm going to draw this in black. So I'm going to let this circle represent my heat engine. And here's what a heat engine does. There's always some sort of what's called hot source that the heat engine works from. I'm going to let this box represent that. I'll go through each case here what the hot source is here in a minute. And what the heat engine does is, oops, let me get this a little further away here. Oops, just want a little more room. There we go. What the heat engine does is it takes heat from some sort of hot source. That's usually called Q sub H, heat from the hot source. You get work out of the heat engine, but you always also have to exhaust some heat to a cold source. That's usually called Q sub C. So this is just a general kind of schematic for how a heat engine works. It's not an actual picture of a heat engine. The heat engine is supposed to be represented by the circle here. So in this case, it's basically the person's body. In this case, it's the rocket engine. In this case, it's the engine within the guts of the ship here that converts the combustion of the coal to work. And in this case, it's the automobile engine. The hot source for all of these cases. I'll go back to the car. When the fuel is combusted inside of the piston cylinder assembly, there's your heat transfer. There's your hot source, the combustion of the fuel. So that's what this would be for the car example. In the steamship example, basically the same deal. When the coal is combusted, or whatever fuel they're using to drive this ship, there's your heat transfer. There's your heat from a hot source. Combustion of the rocket fuel, same thing. Combustion of the calories within this person, same thing. Okay, work being done. Ultimately, the role of the motor is to push the car down the road. So it creates this force, car starts moving, there's your distance, work done. Basically same thing here. I'll say we create forces to turn the propeller, then when the propeller turns, there's your work done. The rocket engine creates a force upward on the ship, or on the rocket, then the rocket starts moving, there's your work done. The person's pushing down on the pedal, and then the pedal moves. There's your work being done. So you notice there's work done in all of these cases. And that work is an output to the system. As far as these systems are all concerned, this work is an energy output, right? The rocket will eventually run out of fuel. Same thing with the boat. Same thing with the car. This young person here on the bike will eventually kind of run out of gas, so to speak, as well. Right? The Q sub C's. Car has to have an exhaust. That is going to carry heat with it. Same thing with the boat. Again, these things here, they cannot function without that exhaust. Everybody's probably seen in the movies where they stick a banana in the tailpipe or something. If you cut off the exhaust of the automobile engine, it will not run anymore. That's not just movies. That's a fact. Same thing here. If we somehow try to cap this and we don't let this air out, this thing will not run anymore. Same thing here. If this hot fuel air mixture is not allowed to leave out the bottom, there will be no thrust created by the engine. And imagine here, if the person quits breathing, they quit exhaling, this system will also quit working. So every one of these systems has to have every one of these three things. So there's some equations we can write for a heat engine, and they're very simple equations. The first one is just a basic energy conservation. When we take a look at what's coming in, whatever comes in has to go out. Remember, energy can't be created or destroyed. All that mankind is capable of is converting energy from one form to another. The heat engine itself does not create energy. It converts heat, the incoming energy, to work. So the equation we can write for this heat engine is whatever comes in, which is Q sub H, has to equal whatever comes out, which is the work plus the Q sub C term. Now, another equation we can write for the heat engine is to describe what's called its efficiency. Efficiency in general is your output over input, or energy output over energy input. In this example, what we're trying to get out of the heat engine is the work. And the energy input is the Q sub H. This is what we would have to pay for. This would have dollar signs attached to it. Now, the work term, you'll notice from what I'll call equation 1 here, if I solve this for work, it would equal Q sub H minus Q sub C. I'm going to go ahead and make that substitution. And you'll notice if I separate these out into the two different fractions, Q sub H over Q sub H is 1. And and we get another equation here for the efficiency. An important thing to realize about this equation, this value here has to be strictly less than 1, not less than or equal to. The only way your efficiency could equal 1 is if this were 0. But none of these systems will work without the exhaust. Again, go through them. If I plug this up, the engine will quit working. Plug this up, eventually this fire will stop. Same thing here, same thing here. This person will have real bad problems if we don't have, if they're not exhausting any heat. So there's other thermodynamic laws that I'm going to talk about with regard to heat engines. I'm going to save that for another video because I see this one's pushing 11 minutes. For now, I will just say this. All heat engines have to have a Q sub C. They will not function without it. And that means that the efficiency of all heat engines is strictly less than 1. It's not physically possible to have a heat engine that runs at 100% efficiency. So again, this video is just meant to be an introductory video on heat engines. I think that I'm over 11 minutes, so I think what I'll do is just pause it right there. I hope that this has successfully introduced the concept to you. Have a great day.